So you want me to start or?
Yes, please.
Okay.
I've just started the recording as well.
All right, great. Well, welcome everybody. And my name is Stefan Bon. I'm a professor in the chemistry department, but I'm a chemical engineer. And I'm going to talk to you about plastic particles, basically. Well, if you want to look at our activities, you can look at our website, which is bonlab.info, or you can follow us on Twitter, or you can contact us via Telegram. So, and hopefully I can give you a little bit of a snapshot of what we're doing, basically. So the topic of today, plastic particles, or as I would like to call them, polymer colloids. And we'll explain a little bit what we mean with that. So first of all, just show you, I've got a really dynamic team of people that do very interesting science in collaboration with lots of different companies. And this picture was actually taken more than a year ago when we didn't have a COVID lockdown. As you can see, it's quite a diverse group of people. And yeah, as I said, we work on lots of different things. So without further ado, I call them polymer colloids. What do I mean with the term colloid? Well, if you look into a dictionary or if you look on Google, you can probably find out that colloid is derived from an ancient Greek word, colloides, and which is basically a combination of two words. The first bit, kolla, which means glue, and the second bit, eidos, which means form. So like kind of a bit like a glue-like form. And in Greek ancient times, colloides was used already to describe gummy, sticky, elastic type of materials. And already then, some really interesting materials could be made. Now, if we then fast forward and we look into the scientific literature, the first time I could find the word colloid in a scientific book was actually in 1805, and it was described in a book in 1846 by Walter Hale Walsh. And there he already said that a French doctor mentioned the word colloid. And in that particular case, it related to disease, to cancer, and he found that certain tumors had like a jelly-like substance, and that jelly-like behavior was referred to as colloidal behavior. Now, moving a little bit further on, since there was some discrepancy about what the word actually meant and what the properties actually were, people came to an agreement in the early 1900s about what a colloidal material would be. So at the turn of that century, the term colloid and colloidal has evolved, and basically this is how we see it nowadays. So in essence, we are saying that a colloidal material, or that colloids, are phase-separated systems in which one phase is dispersed in another. And I'll give you a few examples just to illustrate that. But what's very important is that the dimensions of this phase separation are really small. So typically we're talking about things that are smaller than a micrometer. And if you don't exactly know how small that is, you take a 5p coin, you put it on a side, and you slice it into 1700 slices. And one of those slices then would have the thickness of 1 micrometer. So here you see a little bit of a classification. If we take the three phases, which you kind of know from physical science, you have gas, liquid, and solid. And in the dispersed phase, we have gas, liquid, and solid. And then you can look at typical materials that have one phase dispersed in the other and how they behave. Now, we know hopefully that all gases are miscible in each other, so we cannot really have a colloidal system there. But, for example, if we would have a gas dispersed in a liquid, well, a typical example would be whipped cream or shaving cream, or a gas dispersed in a solid. A styrofoam cup would be a really good example. A liquid in a liquid, for example, could be milk or mayonnaise, or a liquid in a gas, really trendy now, well, trendy for the right way, obviously, is water droplets, a liquid aerosol that hopefully doesn't contain any COVID in this particular case. But liquid aerosols are a typical example also of a colloidal type of material. And then the original one was this jelly-like substance, a liquid dispersed in a solid matrix. That's a gel. And then, if we go to food science, you can think of agar gel or gelatin type of objects or cakes or jellies that you can eat. Now, solid in a liquid, for example, certain coatings or pigmented ink, and a solid in a solid. Tinted glass, so medieval glass, often has solid particles dispersed. They're very, very small and they interact with light to give it a characteristic color. So those are typical examples of colloidal systems, and we would like to focus now on one particular type of colloidal system, and that is polymer particles or plastic particles. Now, you may or you may not know that in nature, these polymer particles exist. And a really interesting example is that of a polymer latex. And a polymer latex, as you see here in the picture on the top left, can be tapped off from a latex tree so that white sap is tiny little particles dispersed in a water-like environment. And when you look at the world map, you'll see that these trees typically grow in, well, subtropical regions. And there again, you know, these are grown commercially, they're harvested and then turned into products, all type of rubber products. And these rubber products, they've been there for thousands of years already. So the Mesoamericans, you know, more than, well, in a period before Christ even already, they already managed to extract this sap from this tree and turn it into all type of interesting products. Now, down here, you see the chemical structure of the natural polymer latex, these plastic particles that are dispersed into this milky white substance. And you see here, for the people that are interested into this, this is typical molecule which is called polyisoprene. And what you then can do is that you can make a material out of this latex and you can then functionalize it further by reacting things with this double bond over here. And like a typical material for which this is used is, for example, car tires or, well, medical gloves, or the examples go on and on and on. Well, a recent development is that not only do these latexes grow inside trees, they also grow in dandelions, and dandelions can grow anywhere in the world apart from the Sahara maybe. And over there, it's also an interesting way of harvesting naturally these type of materials. Now, around the 1920s, people realized that we could also synthetically mimic these materials, or maybe even make a polymer latex that would outperform the natural one. And that was done via a process called emulsion polymerization. So what do we effectively end up with? One of these particles is just like kind of a bit of a pot noodle with 1,000, 2,000, 5,000, 10,000 polymeric chains that are wrapped up like I've tried to depict over here. And then the diameter of one of these particles, and remember these particles are dispersed in water, typically in commercial applications is between 30 nanometer and 800 nanometer. Yeah, so that's how you should imagine what this latex particle, this natural latex particle, but also the synthetic ones should look like. Now, how do we make them in the lab? Well, here on the right-hand side, you see one of my team members, Matt, in one of our emulsion polymerization reactors. So we have this kind of double-walled jacketed reactor that's thermostated here with a water circulating bath. We have a stirrer into the system. We have some feed pumps, and we really nicely can make these type of latex particles, but then synthetically. Now, commercially, these things are done on a way bigger scale, and on the left-hand side, you see a typical batch reactor in an industrial environment, and typically you're making 30,000 liters, 50,000 liters in one go, and the biggest ones in the world, they produce about 150,000 liters in one go. So you make vast amounts of these particles. Now, if you then would get rid of the water and you would look at them under an electron microscope, you can indeed see that they are tiny little spheres of plastic, tiny little plastic particles. And this is what they look like under a scanning electron microscope. So here you see one that we would call have a very broad particle size distribution. And you can clearly see that the diameters of these plastic spheres are all different in this particular way. Now, depending on what chemistry you use, you can vary the properties. You can make them very hard, you can make them very soft, you can give them a certain functionality. And with that, you can then start using this polymer latex. And a polymer latex would be that these small particles are dispersed in water for a range of applications. And I just would like to illustrate a few of these applications for all of you. So here, as I said, these particles, they're wrapped up like a pot noodle. So maybe we can kind of bring them back to where they originally were. So here you see a latex. We dilute it with more water. And as you can see, the viscosity of it, the consistency, it's very easy to stir around. And that kind of makes sense because I just have these plastic spheres that are wrapped up and they just bounce around in water. Now, if I now add a reagent, in this case, it's just base, sodium hydroxide. In this particular example, my latex particles had acid functional groups, and these acid functional groups can deprotonate. And what then happens is that my noodle-like particle unravels itself and dissolves into the water. And what I end up with is effectively large polymer molecules that are dissolved in water, like spaghetti in a way, yeah. So like pot noodle, yeah. You add a bit of water, and what you then see is that the viscosity or the ability to stir it, the viscosity really goes up a lot. So in the end, you can even make a gel, and that's what you see here. Now, you might wonder, what is this particular material used for? Well, a trendy one at the moment, hand sanitizers. A little bit of that plastic is in there to give you the consistency of a gel-like material. Now, then another really interesting property is the viscosity of these little ping pong balls. So for example, if you would like to use it as a paint, if you wouldn't touch the material, you kind of want the viscosity to be relatively high. So if you would paint a vertical wall with it, that it wouldn't drip down the wall. However, if you actually are painting, you want the viscosity go down. So if you apply a force to it, you can get an effect which is called shear thinning, so the viscosity drops. And then for certain type of systems, if you go to very high deformation rates, you might get an effect which is called shear thickening, in which the material actually gets a really high viscosity and starts to behave like a solid. So here's a little video demonstrating the latter. So I can pour it, which is like a little bit of shear, and the material really nicely acts like a liquid. I can then go in with a glass rod, and if I do that carefully, the material acts like a liquid. However, if I apply a higher force, what will happen is that the material acts like a solid, and I can actually lift up the polymer latex from the table. Now, so we talked about these particles in water, we talked about some interesting properties, and here is a very important one for a range of applications that we'll illustrate later. So what you see is that if these particles are in water, we can evaporate the water, and then these particles will all stack on top of each other. Now, if these particles are soft, they will start to deform. And if they're really soft, then all the individual molecules start to intertwine. And then at the end, what we'll have is just a thin plastic film that lies on the underlying surface. So in other words, if we would do that, that process is called film formation. And here you see another picture with the same illustration. Here again, you see this kind of particle that in this case has just lots of colored threads. And you can imagine if they can fuse, these threads can move and these threads can intertwine with each other. And then the end result will be you have a plastic film lying on a surface in which the original dimensions of the particles are completely faded out. So here again, you see a scanning electron microscopy picture of these particles stacked on top of each other, but they haven't film formed yet. So they are still in the spherical shape. They haven't gone through this process yet that they're all intertwined. Now, if you typically use an acrylic paint, for example, to paint your house, then that's exactly what happens. But also if you, for example, make gloves or condoms, that's also what happens. So here I'll show you a little video on how that works. So what you do is you get a ceramic mold, in this case a hand, and you dip it in a solution that contains a salt. Now, that salt then gets dried in an oven onto the ceramic glove. And what that salt does is that it really facilitates the latex particles to stick to that ceramic mold and really form a tight film of coagulated particles, like we saw in that little SEM picture before. So here you see you dip it. So it's nicely dipped. We just added some color to it just to facilitate and visualize what it would look like. And then again, it goes back in the oven for about 3 minutes at 70 degrees. Now, then you'll take it out, and there is your glove. So this is, in a nutshell, very, very quickly how you can make a glove. And then these latex particles now have film formed, so they form a mechanically coherent film, and you can just strip it off the ceramic former, and there you go. A tiny little glove has been made in literally a few minutes. Now, then in a nutshell, you might think, well, what are these polymer particles currently used for? Well, loads of different applications that you may or you may not know. So here on the outer left, you see fabric, non-woven fabric. So for example, fabric tiles or carpet or even clothing that has been impregnated with these polymer particles to give more durable properties. Most adhesives that are used, so stickers or labels on bottles, are made from these polymer particles. Acrylic paint, talked about it a little bit already, so all your household paints, your decorative paints, the ones that are based on waterborne formulations are made from these polymer particles that then act like a binder to glue all the pigments on your wall. Concrete will have these polymer particles in it, and tile adhesives will have these polymer particles in it to effectively have superior properties for the concrete. Your roads you walk on and you drive on will have these polymer particles in it to glue effectively the asphalt better together. Again, what I already said, how you make surgical gloves or any form of gloves or condoms, they're made via dip coating, again, from these latex particles. Then lots of diagnostic tests in the hospital are based on this type of technology. And then something which you may or may not expect is that paper, so here you see a scanning electron microscopy picture of paper. Paper, all these bits in paper, so the paper fiber and the pigments are held together by plastic particles, and often for white paper, when you write on it, it contains a top layer of plastic particles so that you are able to write on it, and not that it's like a filter paper that when you write on it, when your pen, immediately the ink goes everywhere. So, in a nutshell, hopefully I've told you a little bit about plastic particles, what the natural equivalent is and what the synthetic ones are, and in what current products they're going. Thank you very much for listening, and I hope you enjoyed it.
Thank you so much, Stefan. It's been really lovely.
Thanks. So if people have any questions, ask ahead or contact us via Twitter or via Telegram or just drop us an email. Yeah, that'll be great.
I'm going to stop the recording.